All right, recording is rolling. It's Tuesday, April 18th. We're a few minutes into class because I played a few video demos for you guys. You guys saw the train paradox. So if the train is moving at a relativistic speed, what is the length of the train? Well, yesterday, you guys remember we were looking at this length contraction idea. Right? So actually, we were specifically looking at like trains and rockets, right? And then this length contraction. So say a train going into a mountain tunnel, right, would appear to be shorter from the frame of reference of someone outside the tunnel. That's what they're saying in this video. They have this whole example of they're walking through. But remember though that if you're on board that train moving at a relativistic speed, like near the speed of light, you don't notice anything weird about any of these effects on board the train. You don't see the clock ticking any differently than you look at the clock on the wall. If you're traveling along with it, it looks like 1 second per second. If you break out a ruler, a meter stick and measure the length of the train, it all looks completely normal in your frame of reference. But from an outside frame of reference, the train appears to be shorter, right? And for that matter, if you could see a clock ticking on the wall, it would look like it was ticking very slowly, right? That's like the twin paradox we were looking at yesterday. Okay, so we're looking at that one. I showed you guys a GPS, so global positioning system, how that works, and they actually have to take into account both special and general relativity. Otherwise, the times wouldn't work and it would fall apart, right? Or if, I guess alternatively, if people had never come across their theory of relativity and had gotten around to inventing GPS, just the clocks would be off and they would have to adjust them and just not understand why that was the case. Right? I showed you guys this derivation from minute physics. Right? And I gave you guys a page that we're going to take a couple of days to solve from. Right? So you guys got this page up? Okay. Now, the back side of this page involves that Fizeau cogwheel that told you guys about yesterday. We're going to save that for another day. Okay. I should tell you guys too, tomorrow I'm going to pull up a Kahoot with some conceptual questions related to relativity. Can you guys bring your laptops tomorrow? You guys bring your laptops tomorrow so we can do Kahoot? Okay. All right. And then, see if you guys can follow the conceptual questions based on what we did yesterday and today. Right. Right. So we're gonna solve some math type puzzles, right? Like those dilation equations. Oh, look, they're right here, right? Here's time dilation. Here's length dilation. Here's I was saying momentum dilation. Here I have it listed as mass dilation. Sometimes it's perspective. You could think of it like that, right? And then here's mass energy equivalence that you guys just saw derived also from special relativity, right? So we got all these, right? Right, and we're going to take these expressions and solve these relativity questions. Right? Guys good? What we're doing? Right, so just like normal, everybody has different numbers. As I'm going along the notes, your numbers are probably going to be different from my numbers, but we're all solving the same stories with the same processes, right? Guys got that? And so the first three questions all relate to the twin paradox, or at least I was trying to build that story in, right? For some of these works, for one of these, okay. We'll get there when we get there. And so the first question, Earth twin stays on Earth, rocket twin takes off in a rocket and flies close to the speed of light. That'd be like a relativistic speed, right? Sounds like twin paradox scenario from yesterday. In this scenario, when the two meet, what amount of time does Earth twin feel has passed, right? So they're both watching the clock on the wall. Now, Earth twin's looking at his Earth clock saying, oh, it's 1 second per second. Rocket twin is looking at his clock on his rocket wall and saying, oh, it's 1 second per second. In each of their own frames of reference, they don't notice anything weird, right? But if rocket twin's been flying around at close to the speed of light, comes back and meets Earth twin, guys, yesterday, which twin got really old and which twin stayed really young? Earth twin got old. You guys remember that? Earth twin got old, right? So whose clock is beating faster? Earth twin, right? So Earth twin's clock is like tick, 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 1 second per second. But if Earth twin could like look through a telescope and see a clock on the wall of rocket twin's rocket, right? What Earth twin would see is something like this: tick, tick, tick. Right? Again, if you're along for the ride with rocket twin, you don't notice anything weird. But from Earth twin's frame of reference, that's what would be going on. Okay? Right. So I've got two different time values. There's T and T naught, and I told you guys yesterday how these match up is T naught refers to rocket twins frame of reference, and the solid T is Earth twin's frame of reference. Okay. So if rocket twin's been flying around for, okay, now my paper says 5 years. Everybody has a different number, right? So if rocket twin's been flying around for 5 years, then is Earth twin going to say that's more than or less than 5 years have elapsed? got to be more than 5 years, right? That's why it's like getting old. Okay. Now this one I think is pretty straightforward the way it's set up because there's no algebra involved. It's just arithmetic. Now, so some of the other ones are some algebra, but one at a time here. So the time elapsed on Earth is equal to rocket twins time divided by this Lorentz factor, 1 minus v squared on c squared. Okay. Right, you guys remember v is the speed of the rocket and c is the speed of light. Okay, you guys remember all that? Okay. Again, this one, you can just plug in the numbers and get the answer. So the time elapsed on Earth is, okay, now mine is 5 years divided by square root 1 minus, okay. Now this rocket I have going this fast, 2.7 times 10 to the 8 meters per second. You guys probably have a different number. Okay. Square that and divide by the speed of light is listed right here, 3 times 10 to the 8 meters per second, and then square that. Okay. And then make sure that's all grouped underneath the radical. Okay. That's all. Right. Now, let me give you guys a little bit of a shortcut, or you may have noticed this already. Guys, 10 to the 8 over 10 to the 8. Even the fact that it's being squared, does that cancel? Yeah, there you go. So in your calculator, can you just ignore the 10 to the 8 part? I could do like 2.7 squared divided by 3.0 squared. Okay. I gave everybody a relativistic speed, so that the 10 to the 8 should cancel out. Right, you guys all got that? All right. I wonder how much time Earth twin says has gone by. So I'm gonna take my 5 years, divide by. Actually, here, if you want to plug this all in calculator in one go ahead. Some students struggle with that. I mean, this is a good skill to have to be able to plug in a calculator. Here, let me show you how I would plug it in first. Right, square root. Right, it gives me a parenthesis. I want to make sure everything's grouped in parentheses. I might throw in an extra parenthesis just to be safe. 1 minus open parenthesis 2.7 squared divided by 3.0 squared. Right, so I'm getting an answer of 11.47 years. Let me skip some space here and do t equals 11.47 years. Okay. If you're struggling with that or you're getting like domain error, or if it says domain error, you probably put a parenthesis in the wrong place, or there could be one of a number of things you do. Right? You could throw in a middle step. You could chunk this into smaller parts. You could take this fraction right here inside the radical and do that first. And that would look like this. T equals 5 years divided by square root 1 minus. Okay. And then what is 2.7 squared divided by 3.0 squared? Okay. That is 0.81. I could do like that. Right? I could do like that. Okay. Right. So what is 5 divided by square root 1 minus 0.81? Right. Oh, it's the same thing. Right. So if you want to throw in a middle step where you chunk this into smaller parts, you can. Right? Or if you're comfortable with just plugging that all in your calculator in one go, then you can do that too. Either way, you get the same answer. All right. Everybody got on number 1? All right. So time dilation. No algebra, just arithmetic. Okay. You guys ready for number 2? Number 2? All right. All right. Okay. This one is a little weird. I should change the story, but I'm trying to stick with the twin paradox story. Okay. Now this has to do with momentum dilation, or on this paper says mass dilation, but we're just gonna run with it. Okay. Really similar idea. Okay. It says Earth twin stays on Earth, rocket twin takes off in a rocket, flies close to the speed of light. It's relativistic speed. Okay. Given rocket twin's mass according to Earth twin's frame of reference, what was the original mass of rocket twin on Earth? Okay. So rocket twin stands on Earth and gets its mass. In fact, if they're twins, maybe they have like the same mass, right? Or probably pretty close. Right. So like so many kilograms. Great. Takes off in a rocket, flies around. Now there's this relativistic mass dilation. Okay. And the formula for it is the exact same structure as time dilation, right? Or on this paper, I have momentum, but again, same idea. Right? You guys see it's the exact same structure, right? So, well, okay. Now, the story I shouldn't have done Earth twin, rocket twin, because that's kind of a, like, how do you get like rocket twin's mass from Earth twin's point of view, right? But there is a real application of this that particle physicists work with all the time. Okay? And it's over at a synchrotron called the Large Hadron Collider. So let me just give you the story, because this would have been a better story to go with. Right? It's over in Switzerland. Okay? In fact, it's so big, it's like many, many kilometers in circumference. I think I want to say 17 kilometers circumference, I think, so something like that. Right? It actually crosses under the border even with France. Right? So it's a huge synchrotron. Right? And they load in these protons. Right? So they take hydrogen atoms, strip away the electrons. They have these protons, and they fly them around at close to the speed of light. It's like 99.9 something percent speed of light. Right? Now, you guys remember from this graph yesterday, relativistic momentum, that as you're approaching the speed of light, that's like getting like about the speed right here, right? Your momentum or perceived mass is getting really, really huge. So the magnetic field that it takes to keep these protons in a circular pattern, like to act as a centripetal force, okay, has to push as if there's more mass than they loaded in the first place. So they might put in like 1 gram of, I'm just gonna make up numbers. They might put in like 1 gram protons, and then as they're flying around, it's as if there's like 20 grams of protons, right? Like where'd all this extra mass come from? But it's a dilation effect of special relativity. Okay, you guys get that concept, right? So let's go back to Earth twin and rocket twin and just sort of apply the same concept to these guys, right? So let's say Earth twin is somehow able to ascertain mass. Oh, wow, it's kind of like you're 100 kilograms, right? Right. Well, what actually is the true rest mass of rocket twin? Okay. Now this is going to require just one step of algebra. So I'll walk you guys through it. In fact, if you know what you're doing, if you guys can stay a step ahead of me, that's always been a good practice. I usually tell you guys that too, right? If you can stay a step ahead of me. But here's the formula. So mass perceived by Earth twin is rest mass of rocket twin divided by Lorentz factor. Okay. Square root 1 minus v squared on c squared. Okay. Right. And this time we're solving for what is the rest mass of rocket twin. Right? That's to say, like when he goes back up to meets his twin, if they're just standing side by side, right? What's mass then? So do you guys see the one algebra step is to take the square root and cross multiply it? So the rest mass is the dilated mass times the square root. Right? Is that going to be the case? Right, guys good? Right. Okay, and then all we have to do is plug in values. Right, so the rest mass is, okay, now my dilated mass says 100 kilograms, so I'm going to put 100 kilograms. Your number is probably different than mine. Right, times square root, okay, 1 minus, okay, and then, I have this relativistic speed. 9 times 10 to the 8 meters per second, compared to 3.0 times 10 to the 8 meters per second. And don't forget to square those speeds, right? That's part of the process. And this is all being square rooted, so make sure that's all in parentheses too. Okay, just like that. Okay. Now, if you can put that in your calculator, go ahead. Okay. Need a little simplification, then you could scratch out 10 to the 8 because it's on the top and the bottom, even though it's squared, but it's squared both places, so it still cancels out. In fact, if you want to check this down to a smaller step, you could do something like this. Take the dilated mass, multiply it by square root of 1 minus, and then just do all this first, right? What is that divided by that? Okay. It's like, wait. You like chunk this down to smaller parts if you like, right? All right. And now I found the true rest mass of rocket twin. So if rocket twin brought a bathroom scale with him, maybe he's like, I don't know, like accelerating at 9.8 meters per second squared, so he could like stay on the scale and like as if he's on Earth, right? He has like this mass, right? It's like a weight type example, but you guys get the idea. Right? Okay, you guys got that? Pretty good. All right, got one more with the twin paradox story. Number 3. Now, this one, I'm going to forewarn you guys that it's set up in such a way that there's a lot of algebra steps involved. Okay? But this one actually is a pretty cool example. Number 2 is, maybe I should have gone with synchrotron, but number 3 is a pretty cool example. So Earth twin stays on Earth, rocket twin takes off in a rocket, flies close to the speed of light. Earth twin pulls out a telescope and watches rocket twin and views a shortened rocket. Hey, that reminds me of that train paradox that you guys just saw, the train going into the tunnel. Remember, it appeared to get shorter, but only from an outsider's frame of reference. Right? Well, Earth Twin is now looking through a telescope and says, "Whoa, what happened to your rocket? It's super short." Right? Now, of course, if you're on board the rocket, you don't notice anything weird. Everything's perfectly fine on the rocket. Right? Maybe you look back at Earth and say, Earth looks all like flat or something, right? So given the differing perceptions of the length of the rocket, what is the speed that Rocket Twin is moving? There is some particular speed that's going to correspond to this exact shortening of the rocket. Right? Like my numbers are, the rest length is 8 meters. So before the rocket took off, they both pulled out to meter 6 and measured it. Yep, it's 8 meters, and everybody agrees it's 8 meters. Then he flies close to the speed of light. How fast? We don't know. That's what we're solving for. Right? Such that Earth Twin pulls out his telescope and says, "Whoa, why is your rocket only 3 meters long? I thought it was 8 meters. Now it's only 3 meters." Right? You guys get the concept? Right? All right. So here we go. Right. Again, this is going to be a lot of algebra steps here. So the dilated length, like a contraction, is equal to the rest length times the Lorentz factor. 1 minus v squared on c squared. Okay. So we're starting with that. And the question is, what is the speed of the rocket? If you know everything else, you know what the speed of light is, you know the two different perceptions of length. Okay. You guys see it's going to be a lot of algebra steps to sort of like unbury that V. You see that? Okay. Now, again, if you guys can stay a couple steps ahead of me, awesome. I'm trying to give you guys a bit of a head start here. Okay. I'm actually going to solve this in terms of variables. You can plug in numbers whenever you like, but I'm going to solve in terms of variables. So I'm going to divide the L naught down. And this is a good practice to be able to do before you graduate high school, right? Be able to solve algebra like this. Right? I'm going to square both sides. Right? Okay, I have something equals something minus something. What on top of this b? Maybe I could add this part over and subtract the L's over, right? So that would be like b squared on c squared equals 1 minus L on L naught. Right? That could be like that, right? Would it be the same thing? If you like, you could do L squared on L naught squared. Try and match this format. Okay, are we good? Okay. Then I'm 2 algebra steps away from isolating this v. I can cross multiply the c squared. So v squared is c squared times all this stuff. Okay. And then finally, take the square root both sides. Okay. Square root is c squared is just c. So I got c times the square root. Ooh, this sure does look like a Lorentz factor itself too, doesn't it? Okay. I mean, it's that type format. Okay. I mean, the final structure of an expression that we can use to answer the question looks a lot like the original structure. It's just things are rearranged a bit. Okay. All right, so there you go. Just got some algebra. Okay. All right, so let's plug in some numbers. So the speed is 3 times 10 to the 8 meters per second is the speed of light. There's your speed of light right there. Right. Times square root of 1 minus, okay, now the lengths. Now my lengths were, the rest length was 8 meters for me, but the perceived length through the telescope, Earth Twin said, hey, what, you're only like 3 meters long. Okay. So, and I got to square this. Oops, square this, square. Okay. All right. I'm gonna throw in a middle step. You don't have to do this, but 3 times 10 to the 8 meters per second. Okay. You could, if you like, chunk this into a smaller part. So what's 3 squared on 8 squared? Right. It's like 0.1406, like that. Right. Don't have to do that step, but you could. So what is all this? Right. So 3. I'm going to take the 10 to the 8 and just bring that out and just save that in my answer later. So I'll just do 3 times. Okay, square root 1 minus 3 squared on 8 squared. Okay. And I'm getting 2.78 on my calculator screen. I left out the 10 to the 8, so I'll just go ahead and type that back in now. The unit is meter per second. So boom, there you go. Right. Of course, the fastest speed you could have would Yeah, go. Would be like up to the speed of light, right? So this is getting pretty close there, getting pretty close to the speed of light. That's why there's this like crazy length contraction. Okay, all right, you guys following that? Okay. Is everybody getting a number on their paper? Right. Okay. It's working out for you guys. All right, okay. All right. Uh, Number 4 says, given the amount of mass that's converted into energy by a nuclear reaction, how many joules of energy have been produced? Okay. Okay, so I gave you some amount of mass that's being completely converted into energy, right, by some nuclear reaction, right? Maybe you had some uranium, for example, and then you run the reaction and this much mass is missing, right? Or maybe you had this much mass to start with and you combine it completely with antimatter, or however you do it, right? That much mass is being converted to energy. How much energy we talk about? Okay. So this is mass energy equivalence. Here's your E equals mc squared, right? For that. Right, so how much energy are we talking about? Right, well, take your mass, your rest mass. So I got this many kilograms. Okay. Multiply by the speed of light squared. Right? And that'll represent the number of joules. Okay. Now, this is going to be a crazy big number. Like the speed of light itself is already insanely huge. Okay. We're squaring that, it's going to be even bigger, right? And then multiplying by some mass. Right? Like you guys have seen this before. This is the we talked about nuclear energy, I think, a few weeks back. So there's an enormous amount of energy you can get from nuclear energy, and this is the math to back that up. Okay. So I'm looking at crazy, crazy huge number of joules. It's like 10 to the 17 joules. That's what I'm looking at. Okay. You guys getting a large number on yours too? That's also matching one of your answer choices? I said something like that? Okay. Now, that number is so insanely big. It's good to put some context to it. Like if you were to, yeah, you could convert it to like kilowatt hours if that helped possibly, or like megawatt hours. You could say, well, if you were to use that energy at some rate, or if like a whole community of people were to use the energy at some rate, like how long would it last? Okay. Now, question number 6 actually gets at that framing. Right? So question number 6, we're going to start out the same way, and then we're going to do some dimensional analysis and say, well, how long would that actually last? Right? You guys get that concept? Okay. We're going to save that one for probably tomorrow, though. Okay. All right. Are we good so far? All right. All right. So mass energy equivalence there. All right. We're going to do just a couple more today. Okay. All right. So it's the 2 at the bottom of the page, number 5 and number 12. You guys see number 5 and number 12? So number 5, where does time tick faster due to special relativity? Remember, special relativity is relativity due to motion. Right? You guys remember rocket twin takes off in a rocket and then like hardly ages at all. So his clock must be ticking slower, right? So between being in a spaceship moving near the speed of light or surface of Earth, whose clock is now ticking faster? Earth. Yeah, Earth twin. Earth twin's the one that got old, right? Isn't that true? Okay. Okay. And number 12, where does time tick faster due to general relativity? Okay. General relativity, that's the one that deals with gravitation, like mass and gravitation. So mass warps space-time. That's this right here. The more massive an object is, the slower that time ticks. Right? The more massive, the slower time ticks. Okay? So that was all incorporated also in that GPS video you saw, right? So like GPS satellites going around the Earth, they have to take into consideration both the fact that they're moving fast, that's special relativity, but also the fact that there's less gravity way out here compared to near the surface of Earth. That's general relativity, right? And both of those effects affect the clocks and therefore affect how that GPS will work. Okay, so where would time tick faster? On the surface of the moon where there's hardly any gravity, or surface of Earth where there's a lot more gravity? Where's it ticking faster? How many of you guys say the moon? Moon? Yeah, because that's where there's less gravity, right? Remember, on Earth, there's more gravity, it's going to tick slower. Right? Gravity, like mass and gravity, slow down time. Okay. Right. You guys got this? Got this? Okay. So we've done about half of them on this page. we're going to save the ones we haven't done yet for probably tomorrow. And also, what I want to do tomorrow is do Kahoot with you guys. So again, you guys are going to bring in your laptops tomorrow, right? So we can do those conceptual questions, right? Any questions from anything today? Any questions? Okay, so we started off with some demos. So let's end with some demos too. We're going to do that.